Okay, so we're gonna jump around the chapter a little bit. We're going up to 11.6, where we have two more tests. So like I said, we have two specific types of series that we know how to analyze if we see that. Otherwise, if it's just sort of generic series, we're going to implement some of these tests. So we had the divergence test, which we said is a very good first step. Take a look at that because it's pretty easy to implement. The problem is, of course, like we said, how it only works one way, so it can be inconclusive. So I'm going to get right into, there's two tests in the section. Ratio test will be the first one. And these tests are, I think students like these because these rely on a formula. So you evaluate something, without, I hate to say it, but you don't have to put a lot of logic or problem solving. You just have to work through the calculation, and then you have your result. They're also very powerful, especially the ratio test. The root test less so, but it works in a lot of situations. And I'm going to be straight with you. The ratio test is a go-to in some of the things that you'll do later in possibly in your mathematical career. So what I'm going to do, I'm going to write out the test, and then I'm going to do some examples, and then I'm going to give some sort of hints as to when you're going to want to use this. Okay, so simply put, the ratio test, what we do is we're given a series where the terms we're going to call an. Then we're going to evaluate the following limit. N goes to infinity of the term n plus 1 over an. Okay, so we evaluate this limit. You'll see it live here in a minute. And we're going to call the result L. So if L is less than 1, then we have what we call absolute convergence, which I'm not going to go into. It's actually a stronger threshold. So it converges, and I'm just going to put absolutely. That doesn't mean it absolutely converges. It has to do with the absolute values would converge as well. If L happens to be greater than 1, the series diverges. That includes going to infinity. This doesn't, well, just so there's no ambiguity, because infinity is not a number, but it's still applicable here. And then unfortunately, you can have this situation again if it happens to equal 1, then it's inconclusive. Okay, so you find the calculation, you get an answer, and your result is plain black and white. So let's see this in action. Okay, you'll see some common things in the calculations. I'll mention those. Let's see here. Example. Okay, so you're looking at an exam. I don't want to do that one first. Okay, let me do a nice simple one to start. Something relatively tame is a first example. Okay, so this is on an exam. Does it converge? Does it diverge? Okay, this isn't one you'd want to play around with the divergence test. So we're going to just go into the ratio test, and later I'll explain why I would think that's a good choice. So I'm just going to state what I'm doing, and I'm just going to dive in and evaluate this limit. So the term an plus 1 is this exact expression, but I'm going to move the n up 1 on the index. So I have n plus 1, and I have 6 to the n plus 1. Likewise, I'll have n over 6 to the n. So 2 points I want to make right off the bat. You see this, you have fraction essentially over a fraction type of a situation. This sort of looks like a Big Mac or something. For every example I do from here on, I am going to write this term, and then I'm going to write the one under it flipped. So they're side by side, but that an that's in the denominator is already flipped. Also, these are absolute value signs. In this particular problem, they serve essentially no purpose, but that is typically not the case. So do not leave these out. Students will have a tendency to ignore them a little bit, but they're going to be of use. So don't leave those out. All right, so now what I was saying, this is what I would typically start a problem like this to look like. Okay, now this is why this works. How many 6's are here? N. How many 6's are on the bottom? N, but one more. So you get cancellation, n of these cancel, and you're left with a single 6 in the denominator. And I'm going to pull that out of the limit. Okay? And I'm going to drop the absolute values as n is positive, and this is a very common situation with these. I'm left with a constant. What is this limit? Well, again, comparing powers of n, they're both power 1, they're the same, leading coefficients 1 to 1, so this limit is 1. So the result of the calculation is 1/6, clearly less than 1, converges. So again, just about writing a solution, I either have to say ratio test here or converges by ratio test here. I need to be clear about what I've done. Also, I would definitely include that piece. Okay, so it's one thing to go through the calculation successfully, but it's another thing to prove your argument. So rules of thumb, always say what test is being used. Don't assume the reader knows what you're doing. Don't ever assume anything. And then explain why this test is showing convergence. This test is showing convergence because the result of this is less than 1. Okay, so that's a nice easy one. A couple more that'll show you some common sort of elements of these. Let's try this one. Another example here. A little bit more involved. Again, the question is, does it converge? Does it diverge? So I have 1 to infinity, and I'll have in the numerator 10 to the n. In the bottom, I have n plus 1. And here I have 4 to the 2n plus 1. Okay, so I'm going to go in with a ratio test. And again, I choose to, instead of writing stacked fractions, I'm going to just flip the one that goes in the denominator. So here's a point I want to make. You go back to this test. In the numerator, we have a n plus 1. That doesn't mean that this is good to go. Essentially, what you need to do for that term is replace n with n plus 1. So here I'll have 10 to the n plus 1. That's no big deal. But this will become n plus 1 plus 1. So that needs to be written this way. And likewise, if that n is n plus 1, then this is 2 times n plus 1 plus 1. So that is 2n plus 3. Okay? Take a good look at that. That's a common thing. Like people will see, oh, that's n plus 1. That's good. No, it's not good. You got to replace the n with the n plus 1. And then the second one is exactly what you have in the series, but of course I'm going to flip it. And 10 to the n. So what you see here, you see in you've seen some common themes, right? You're gonna have some matching items, and there's gonna be cancellation. I'm gonna work vertically. So if I look at the tens, let's start there. 10, n plus 1, 10n, there's an extra 1 on top. N of them cancel, one of them is left over. And then I'm going to write this n plus 1. Okay, what about the 4s? Well, I got 2n plus 3, I got 2n plus 1. So 2n of them will cancel. That means 3 to 1. That means there's 2 4s left down here. 4 squared is 16. That'll go in the bottom. Okay, that takes care of the 4s. N plus 2. I guess I didn't need all that, but that's okay. And again, you see this very common sort of end game. 10 over 16, that's what? What is that, 5/8? Yeah, it took me a second. And again, what's this limit? This limit is 1. So this is 5/8. That is also less than 1. This one converges as well. Keep in mind, like we said, you're not going to know what it converges to. That only really applies to the geometric series. Okay, what else? There's another item to address. Let's try this one. Does the series converge? Does it diverge? N from 1 to infinity. N factorial, this exclamation point, over 100 to the n. To the n. Okay, so again, this is called a factorial. That's a descending multiplication. For example, if you had 5 factorial, that's 5 times 4 times 3 times 2, all the way down to 1. Always down, hitting every integer down to 1. Factorials only apply to integers. So if I have n factorial, how would I write that? Well, I'm going to start at n. What comes next? N minus 1, n minus 2, all the way down to 2 times 1. So you're going to need this for this type of problem. So let's try this one, the ratio test. Get this calculation moving. N plus 1 factorial over 100 to the n plus 1. 100 to the n over n factorial. So again, you look at the 100s. I got n plus 1. There's an extra 1 here. I'll choose to pull that constant out of the limit. Not that you have to, but I just like that. And we have this. Now, what to do with this? So, I'm going to go back to, oh, it's up here. That. Let's think about n factorial. I'm going to write out exactly what I see above there. Okay, well that didn't help much, right? I'm going to do the same thing with n plus 1 factorial. That'll start not at n, but at n plus 1. And if I descend down through, what do I have? N minus 1, n minus 2. I have this. So it looks like a great big mess, but what's beautiful here is you have complete cancellation of all of these factors. So I'm left with this n plus 1. So you're left with this result. That's infinity, not 1. Sorry. Oh, there we go. And as n goes to infinity, this certainly goes to infinity. Okay, so by the conditions of the test, this would be a diverging series. So, as some hints as to when to use this, and I'm going to give you two, and these aren't blanket statements. These are just kind of hints, things to keep in mind. When to use, and this is very kind of general. When you have a ratio, such as this, right? Notice for all of three of these examples, they were all ratios. They had a numerator or a denominator. And why this test is effective is because you have your first ratio here, your second one is kind of the same but flipped, and you get this mass cancellation. Now, that doesn't mean everything that's a ratio needs to be hit with the ratio test. We saw examples the other day which were better done by the divergence test. But if you see, especially when you start to see powers, like when you see 10 to the n and 4n to the something, when you start to see that, that's kind of your indicator, because that's when you get all this cancellation. The other sort of dead giveaway is this thing, the factorial. If you see a factorial, you should have a red flag go off, or not maybe a red flag, but it should pop into your head. Maybe this is ratio test. If you see a factorial and a ratio, that's a no-brainer. Okay? So a little bit algebraically intensive, but you see a lot of the same steps in a lot of these problems. So like I said, I've noticed that students seem to like it. They like the calculation part. So see what you can do with the homework. Okay?